welcome back. In our last lecture, we discussed on the tunneling phenomena or tunneling mechanism or quantum tunneling, how the electrons tunnel between the tip and sample, and the distance between the tip sample plays a very important role to the tunneling current, and tunneling current varies significantly as we change the tip sample distance. And by that we can create the image of the surface that we will see today in the operation mode. There are a couple of operation modes, particularly constant height mode and constant current mode, and these two modes are normally used to get the surface image in the scanning tunneling microscope. In addition to that, I will show you what type of image is obtained in scanning tunneling microscope and how the image is processed briefly, and there can be also some artifacts, how one can know the presence of artifacts on the in the image and how to get rid of those artifacts. So, as per the operating modes concern, we have two modes which are widely used in the scanning tunneling microscope. One is constant height mode and another is constant current mode. So, in the constant height mode, it means the tip is at same height above the sample. The sample is there, we have a tip. So, it should scan, it is a scanning from microscope. So, tip has to scan, and normally it scan from left to right, and again it come back, again left to right, again come back left to right. It will scan like this in a raster manner. So, now tip is maintained at the same height, and in order to maintain the same height, we apply a constant voltage to our piezo scanner, because by applying the voltage we can change the height of the tip, because piezo scanner or piezoelectric materials used in piezo scanner allows it to either contract or expand, and as it contract and expand, the tip goes up or down. So, in these cases we do not make tip to go up and down, rather we make sure the tip is moving at constant height above the sample. As we move at the constant height, what will happen if at any places there is a protrusion or there is a hill on the sample, then our tip will be much closer to the sample surface. If in any places there is a downwards valley, then we will have a larger distance between tip and sample. So, so depending upon the sample height, as you see here, let us say different atoms are there. In these places, the gap between the tip and sample is larger. On the other hand, at this place, the tip between the distance between the tip and sample is smaller. So, when the distance between the tip and sample is smaller, then we will measure a higher tunneling current. When the distance between tip and sample is larger, then we will measure a small tunneling current. So, here we have seen that in constant height mode, tip at constant height and it is scanned above the sample. And then depend as we have a different tunneling current, one places high tunneling current where the distance between tip and sample is small, and other places a less or low tunneling current. This tunneling current can be used for imaging purpose. So, we get the surface topology from the current data or tunneling current data in this case, and moreover this is a fast way of doing, because we do not change the voltage to the piezo scanner. As we do not change the voltage to the piezo scanner, the tip can move at a faster rate. So, it is advantage that we can do scanning very quickly, but also it has a disadvantage is that if sample is very rough, then tip may crash. Once tip crash, then artifacts will be generated, tip shape will be distorted and artifacts will form. So, this type of study can be done for a atomically smooth sample. If we know already that sample is very smooth, then we can use it, this mode. and this mode is can provide atomic resolution image, because directly we measure current in the level of picoampere to nanoampere, and thus it can gives us very high resolution. And another mode is a constant current mode. Constant current mode is used for unknown sample or rough sample. So, here our feedback control will allow or will set a preset a current that it wants to measure only. In order to do that, as you see here, we want to measure a constant current. My tip has to go up and down to see that preset current. If at some places here sample is a little above than this place. So, thus in order to measure constant current, tip has to go a little upward here, but again as you see the tip has to come downward here, because of distance because some sample is seen at a little lower depth. So, in order to measure constant current, tip has to come down, and tip has to come down by suitably applying a voltage to the piezo element. So, our feedback control will pass the information how much current it is seeing, and therefore, how much tip has to come down to see a preset or constant current. In this way, tip has to go up and down to see constant current, and how much tip is going down and how much tip is going up, that will be utilized for constructing the image. And as we are measuring the constant current, we are making sure that tip is not at all going to be touch the sample, because as soon as it come to closer to the sample, it will measure a higher current, and feedback loop will certainly stop the tip moving closer to the sample, because it already measured that much of current. So, feedback loop will give the signal that you are already reaching to the value of the current, now you have to go upward. So, in this way this type of measurements or constant current measurements is particularly done with the unknown sample, and the voltage in the piezoelectric scanner provides the topographic height to construct the image. How much voltage we provide to move the tip upward or downward direction, and that voltage is utilized to construct the image. So, basically we have two modes, constant height mode and constant current mode. Constant height mode is suitable for high resolution image as long as sample is atomically flat. Constant current mode is for unknown samples, it should be done fast, and if the sample is atomically flat or very smooth, then constant height mode can be utilized for that sample. So, now you see how the image look like in scanning tunneling microscope. This is a STM image of highly oriented pyroelectric graphite, HOPG, highly oriented pyroelectric graphite. As we know, the graphite is nothing but hexagonal sheet of carbon. The carbon atoms are arranged hexagonally, and what we see here, you see the hexagons, there is several hexagons. At that place tip measures current. So, therefore, you see the brightness at the place where there is a carbon atoms and there is a bonding, and in the center you see dark, center of the hexagon you see dark, because there is no current available, because there is no atom available, there is no electronic clouds. Therefore, we do not measure any currents at the center of a hexagon, therefore, it is darker. In addition, if you look carefully, mostly we could see that the contrast or brightness is little higher at the corner of the hexagons where carbon atoms are present, because as it is a constant height mode, as tip is moved across the sample, wherever it see an atom, there only it will find some current, and that current is utilized for constructing the image. When at one particular place, let us say it is a hexagon, we have a carbon atom, six carbon atom, so whenever it see a carbon atom, tip is scanning at this position, at this carbon position, it will see a higher current, and that current is plotted used for getting this topographic image clearly showing the hexagon of the graphite HOPG. And as you see now, you can actually measure the distance between carbon atoms and the distance between what is the hexagon diameter, or all kinds of measurements at the atomic level you can do. And this is a monolayer graphene showing the hexagons with a bias voltage, as you see, 0.6 volt and current 0.3 nanoampere. At a current 0.3 constant nanoampere, it is measured in the graphene case. Here is an example of C60 fullerene on mica. In the left side, what you see is a constant height mode measurements. In the constant height mode, at the top of this fullerene molecule, which are like a sphere type of molecules, at the top you see very bright features. Bright means it is measuring a high current, more current, tunneling current, and therefore you see more bright. And in the y axis, it is giving the lateral direction. From the lateral direction, we can see that the diameter of the fullerene was measured to be 0.7 nanometer or 7 angstrom, which is close to the 0.71 angstrom theoretically measured for the C60. And in the height cases, you can also this scale bar showing the height, telling about the height of the sphere, or in this cases fullerene molecule. And in the right side, you see the position of the atoms where the carbon atom are present. For example, carbon atom is present here, it is more bright here, here more bright, here more bright, and one can determine the position of carbon atom from the current graph. And this is the scale of current scale. Wherever the atom is present, there you see the brightness level is more because of higher current or larger current in the current measured by the tip in the STM. So, in these cases, it is a mechanical sheared platinum iridium tip was used. Here tip was prepared mechanically just by simple coating a platinum iridium wire and measured in constant height mode. This is again a topograph of silicon surface, and what we see there is a brightness darkness differences in the sample. It is showing a sphere of something like this type of surface. The bright dots are the protrusions and the darker part are the depressions. By taking a line scan, this is a 5 nanometer by 5 nanometer area of the sample, and this scale giving us the height scale and how much above and how much down in the picometer level. And this is a line scan graph. Line scan graph gives us quantitative information. As we can see here, it is scanning from here, it is beginning from here, it is beginning from here. This region is here, it is looking like a darker, that means low height is low, height is there is in depression, and that would measure a small current. This is almost like a around 70 picometer downwards, and then as soon as a brighter portion comes, this is a upward portion or protrusion, the tip has to go upward, and it has gone upward around like 50 to 150, like it is a height of around 100 picometer. Height of this sphere is 100 picometer above this ground level, and then it has come down. As you see, there is another protrusion downwards depth here, and it is showing downward, and again little bit of up, again little drop up, and then again coming downwards. So, this is done by line scan, and in the imaging image you can just draw a line and see how the up and downwards of the tip is occurring, and thereby measuring the height or depth in the atomic levels. So, this type of height measurements or the vertical jet measurements was not possible in our scanning electron microscope or helium ion microscope, but this scanning probe techniques provides us jet resolution or depth resolution in the atomic scale or in picometer scale, as you see here. This is a 1-1 surface of the silicon, how the atoms are arranged on the surface of the silicon, silicon 1-1 surface. You could clearly see the atomic arrangements using the scanning tunneling microscope. One of the advantage of scanning tunneling microscope is that you can do in any atmosphere, you can do under air, you can do under liquids. This is an example of gold sample, gold 1-1 surface collected 1-1 surface image is collected under the liquid, and in this cases liquid was 5 mm phosphate buffer solution. It was under 5 millimolar phosphate buffer solution at a pH of 7.7. This image was collected in two conditions. One was without air, without argon, and another was with argon protection of the tip. The protection was done just to see what the difference is coming, but actually what is being observed that there is no difference at all when it is done in the inert atmosphere or with a without an inert atmosphere. So, in presence without argon means in presence of oxygen, because it was a aqueous electrolyte solution. So, the oxygen presence in the solution or in the medium has no much impact as far the quality of the image is concerned, and this image was collected using a platinum iridium tip, because platinum iridium tip can be utilized because they are more inert in the solution compared to the tungsten tip, which can form oxide, and once it forms oxide, then the tunneling current measurements cannot be possible because of the low conductivity of oxide. And in this particular cases, measurement was done with a 0.2 nanoampere constant current mode. It is a constant current mode measurement, and with a bias voltage, as you see 0.1 volt, very small bias voltage. And here the potential to the working electrodes was 0.4 versus saturated calorimeter electrode. It was done with the electrochemical cell, where the working electrodes was a gold, and that was put at a potential minus 0.4 volt versus saturated calorimeter electrode. It is important to note that the resolution or the quality of the sample was almost same as that done in ultra high vacuum condition. Normally ultra high vacuum condition is used in many scanning tunneling microscopic images, because in ultra high vacuum we can have a clean surface without having adsorbate or any impurity on the surface. In this type of STM study, we exclusively measure the surface properties at the atomic scale. Therefore, cleanness of surface is very important, but in this particular study, as we see, it is done under liquid. So, without ultra high vacuum also it cannot be possible to do the measurements of liquid in ultra high vacuum, but the information obtained or achieved with gold sample in the liquid medium is almost similar to that of taken in the ultra high vacuum condition, providing the atomic resolution. About the image processing, there are several image processing technology are available. I will not go more detail into image processing, but just a more simple examples I have taken here, like a median filter was used to process the image. In this particular cases, there are 8 pixel, and as you see, in every pixel there are different noise value, there is a different gray value, and but this value, among these value, this is completely something very unusual value of very high value. So, therefore, noise reduction can be possible by taking a median value of 8 pixel. A median value of this 8 pixel was found to be 68. The median value was taken as 68 instead of 255. 255 is replaced by 68. By doing that, one can reduce the noise, could be due to different environmental factor, and this is a noise reduction image before noise and after noise. This was after median filtering of the noise. When noise is removed, as you see, the clarity of the image is improved. So, in this way image processing done, but image processing is depends on the software available with the machine, and therefore, I am not going much detail into it. Data analysis as per the constant, I have discussed about one line scan. This is another example how the line scan is providing the quantitative information. In this case, it was a 3D germanium iron on the surface, and we could see taking a line scan. This red line is a line scan. By taking a line scan, we know that means which region there is a downward direction movement of the sample, and which region there is upward direction of the sample topology. From the left side image, certainly this region is a little darker, indicating that it is downward, but we by microscope from the image we cannot measure how much depth is there. In this there is a depth. This is a downward direction near the island. The surface is going down at the edge of the island. The surface is not the flat, it has come down. So, this measurement, height measurements can be possible, or vertical height measurements can be possible by the scanning probe technique. And in addition to that, we certainly know it is a 3-dimensional image by other microscopic techniques such as SEM and helium ion microscope. In these cases also from the brightness or darkness difference, we can certainly know the 3-dimensional image, but it is very difficult to measure accurate measurement of this height, how much above the surface. That we could do in these cases by measuring a line scan. Exactly from in this particular cases, the height is around 0 to 150 angstrom, that is 15 nanometer. This quantitative value can only be achieved by scanning probe technique, but not in our other technique that we have discussed, scanning electron microscope or scanning ion microscope, though they gives also 3-dimensional image. Quantitative information about the z direction or height direction was not measured by other microscopic technique. Artifacts, the artifacts can be due to several reasons. So, major artifacts comes from the tip. Tip shape significantly affect the image quality, particularly if the tip is blunt or tip is very rough, then the image cannot be correct, or image cannot be the real image. That could be due to artifacts. As you see here in these cases, let us say we have a one-dimensional feature on the sample, one-dimensional feature of the sample, and this type of one-dimensional feature cannot be used, cannot be studied by a tip of this type of tip cannot be used to study one-dimensional feature. So, in order to get the correct image of a one-dimensional feature, our tip should be of similar aspect ratio or better aspect ratio. Aspect ratio is the ratio of the height to the width or thickness, that is aspect ratio. So, if we choose a tip of one-dimensional features, then only it can gives like here by using a tip of green color, we can get a image of one-dimensional feature using the STM. On the other hand, if same one-dimensional feature will be seen by this type of tip, then we will get a image of like this, because as soon as tip comes closer, it cannot come very close to the tip, because otherwise this place will touch, it cannot touch in our STM, because this region will measure current, and therefore, as we provide constant current mode for unknown sample, it will make the tip to go away from the sample, because at these places it will see a larger current, and therefore, it will not allow the tip to touch to the come close to the one-dimensional feature. Therefore, the tip has to go above or away from the sample and providing an image of like this in this kind of tip. Even the feature is original feature is a one-dimensional feature, but using a tip like this triangular tip, we would get a triangular type of features in the image. So, therefore, it is very important to have a tip which is high aspect ratio. In addition to that, this curvature of the tip curvature should be smaller than the curvature of the sample. If the tip curvature is larger, then we cannot get the correct or correct image of the sample. As you see in these cases, there is a features, almost all features are looking similar, and but in the middle there is a brighter features, and around that there is a halo, and these are carbide clusters. What we could see that in addition to the carbide clusters, as you see in the image, in the background there is a one dimensional directional features are seen, and all these particles are appearing of similar shape with a middle portion brighter than around the portion. So, this type of image indicates there is artifact, there is something wrong with the tip, and here this image was collected with a blunt tip or very not sharp tip, giving the showing the image of the tip only, not actual the sample. In the C, you could see those clusters of completely different shape, Here it is larger, and during the scanning we see that in some places the tip touch to the sample, there is a contact between the tip and sample, and thereby there is a change in the tip shape. When the tip will scratch the sample surface, then there will be tip shape changes of the tip, and that is what happened. After the tip shape changes, you see completely different type of features, and this is again not correct, because if we see here some of the particles are appearing as a triangular or something like 3 dots. So, those are not correct, this is due to artifacts. So, these are, if this type of features are seen which are of similar shape throughout the sample with a elongated features etc., this indicates about the artifacts of the tip providing wrong image. And such artifacts again can lead to not provide actual information of the sample. As you see in these cases, tip do not have a very high aspect ratio, therefore, tip cannot come close to the sample. As soon as it starts coming here, it has to go up, because we measure constant current, and thus these regions cannot be actually seen in the image. This region of the sample cannot be seen. These are called dead region, because the tip is very blunt and the curvature is very high. Using a large curvature of the tip, we cannot image the smaller features on the sample, and that are termed as a dead zone. Artifacts can also be due to multiple tips. If the multiple tips are there, then they will show different type of information on the image that you see here. For example, this is a multiple tip, tip number 1, tip number 2, tip number 3, and if there is a single feature here which is not very the height of this feature is not very tall, then we could see the features like this. But as we keep on as the features height increases in the sample, then at that places we see a double tip information. As you see here, the same features looks like 2 repeating features. This is due to the double tip. 2 tips are measuring the current at the same time, measuring the voltage at the same time, because they measure they are being measured at constant current mode. So, these 2 voltage is going to 2 different tip, giving 2 different data points. That is why repeat of this same structure. Here this type of feature see multiple such type of structure, Each of these structure, there is a one feature actually, but each tip is measuring them. As each tip is measuring them, that is why the repeated information are being seen here, multiple tip effect. Each tip is getting information. Here is tip image, even it is a one dimensional feature. What you see here, there is many features because of many such small tips at the tip apex. Artifacts can be also due to the piezoelectric scanner, and particularly due to creep and non-linearity, and we have discussed before what is creep. It is a time dependent phenomena. So, normally here you see there is a bending of the steps in the beginning of the image due to creep of the piezoelectric effect. Into the piezoelectric scanner we provide the voltage, and when we provide the voltage, that will expand or expand or contract. Now, if we are applying the positive potential, that tip has to move expanding, and when we bring back the voltage, so that tip should contract quickly, but it cannot be done. It never act instantaneously. It takes time. It is a time dependent phenomena. So, by the time our voltage has come back to the original position, my tips still will be moving in the right direction, other direction, and that leads to this bending. So, it as piezoelectric scanner do not reflect or react instantaneously, but takes time, and that leads to the creep or due to the distortion image, and in these cases it is bending occurring. Similarly, here you see there is actually this is a single steps, this is a single step, but because of double tip it is appearing as a double steps. It is actually not a double step, but a single steps. As you see, every places the this step, the gap between these 2 points are always same, fixed, indicating it is due to the tip effects, not actually the sample. If it could be double step in the sample, there is a rare chance that every places there will be this step gap will be almost equal. So, in conclusion, constant height mode is prepared for high resolution STM image because it actually measures the current at that same place. A different type of matrix elements and filtering is used to smoothening the images to get more clean image, and to measure the length, width, height or thickness of the layers. The line scan can be utilized to get quantitative values. As we also have seen, the STM tip has a strong effect on the resulting image. The tip has to be atomically sharp and that has to be single tip, otherwise the image will be distorted, or distorted image will be forming because of the distorted tip. In addition to that, we have piezo creep and non-linearity that also leads to distorted image. For getting information about a larger or high aspect ratio feature, the tip has to be also high aspect ratio to provide the correct image. These are the references. Thank you.